Hello everybody. In today's video, in the series Basics of Life, we're looking at habitable zones. What is a habitable zone and how can it be defined, and what are the limits of this definition? First, we will talk about classical habitable zones, short HZ, and then look at extensions or non-classical habitable zones. First, the idea of a habitable zone is you have this green ring, so there is a distance from a star, from a mother star, where water can be on the surface of a planet can be found as liquid. This is more or less the simple definition of a habitable zone. And here in the image we have two different examples. One is the TRAPPIST-1 system and one is the solar system. And as you can see, in the solar system, we know that the Earth is more or less in the middle of the habitable zone. Venus and Mars are at the borders, at the inner and outer borders. Although the thing is, if Mars was a larger planet, it would still have an atmosphere, and if it had an atmosphere, and maybe also a magnetosphere, and then it would have liquid water still, maybe. Whereas for Venus, the water has been cooked away, probably. So it's a very dry planet. So the Earth has been lucky to be in the middle. For the TRAPPIST system, the star is much weaker and the planets are much closer together. So there are up to 4 planets that are in the habitable zone. And as you can see, E and F are in the middle of the habitable zone and D and G on the border. B and C are clearly too close to the star, and H is too far away. So probably in H every water is frozen. In B and C the water is probably cooked away or will cook away permanently. Then there's the distinction between an optimistic and a conservative habitable zone. And this is again what I already told you a little bit. If you have special conditions on a planet, the habitable zone can be a bit larger. If you take just small planets or planets of Earth's mass, then it may be a bit smaller. The thing is also what happens if planets have, for example, elliptic orbits. Do they leave the habitable zones? Things like that. And here you also see that depending on the luminance of the star, the habitable zone will change accordingly. If we look at the star types in the Hertzsprung-Russell diagram, this OB, A, F, G, K, M stars on the mainline stars and the white dwarfs, we can look at the habitable zones because these stars have a typical luminance. For O to A stars, they're not often looked at because they live so shortly that they will blow up or start being unstable very soon, in a couple of million years. So life wouldn't have much time to develop. So they're not very suitable for life. In F stars, the time could be enough to develop one cell life. This is always in comparison to the Earth. We know more or less how long it took on the Earth, but we're not sure if this is the correct time always, but it's the best estimation we have. The conditions on the Earth. The UV is very high, and the stable phase is also relatively short. So F are not absolutely impossible, but unlikely. Then we have G stars like our Sun. And the advantage is that the habitable zone is quite wide in G stars. And the planets don't have to be as close to the stars that they have synchronized rotations to orbits. So planets won't show the same side always to the star, which some people think is a good idea if the planet doesn't do that. Because one side gets very hot, the other side gets very cold. Although there could be strong winds that maybe deal with that, but that's a matter of which model you adhere to. K stars are kind of the best candidates, best compromise between width of the habitable zone, light in the visual range, still a little bit UV, which is good, and very long-lived. So this may be the Goldilocks type of star. Whereas for M types, they're often discussed. These are very small stars and flare stars. So they can have outbreaks, which may help life in the beginning, but also may destroy life. So we don't know exactly if planets around M stars are suitable for life or not. Then somebody calculated if you have a white dwarf. White dwarfs have a luminosity that is roughly 1,000 times weaker than main sequence stars. And the other thing is that they came out of a giant star, and the giant star blew away its surface. So we don't know what that does to planets actually. Very, very theoretically, it could be possible to be in a habitable zone, but this would be very, very close to the star. And it's hard to get there and stay there. That's the point. Then the concept of habitable zones has its limits, clearly. For example, if you have large planets, they have primordial heat in the inside, and this heat could help life. Maybe not higher life as we consider ourselves, but simple one-cell life, most certainly could live in the inside of a large planet, and probably not our large planets from Jupiter to Neptune, because they are liquid and very hot inside, and don't have a stable surface. But in a bit smaller, huge planets, it could be possible. As I already mentioned, atmospheres play an important role. An atmosphere protects a planet and keeps it warm. But it has to be stable, it has to be renewed. And smaller bodies in resonance to other large enough bodies can have tidal heating. Here I'm referring to Io, Europa, Enceladus, Miranda. Three of these four I already mentioned in earlier videos. And as I already shortly mentioned, the eccentricity of orbits is also very important, not only for the stability of the climate, but also for the stability of the planet in a planetary system. Eccentricity is very important. Mercury has an eccentric orbit, and that could one day be his fate, actually, this eccentricity. There are various things that can happen to a planet with an eccentric orbit in a system with more or less circular orbits. Habitats can develop with the life that is on it, and this is something that happened on the Earth. So the atmosphere in the beginning was very different to the oxygen-rich atmosphere we have now. And also the temperature varied a lot on the Earth with the frozen planet, fully frozen planet, and then later a partly frozen planet. And sometimes it was very hot, depending on the distribution of the continents. And also stars may not be stable. Our sun is heating up slowly but continuously. So sometimes ecosystems are able to compensate. And this is also what is called Gaia hypothesis, that the whole ecosystem could react to changes. Maybe rather to slow changes than to fast changes. And the most important, last but not least, point for habitable zones is it's clearly different for simple life forms than for complex life forms, because simple life forms can live in almost any extreme environment. We will talk about this in a later video, but just to make you curious, one animal that can survive in very, very harsh environments, for example, is this little thing. Yeah, the tardigrade is it called in English. I always forget the English name. Very small animal that can survive in highly radioactive or ultraviolet or very cold environments by switching into a survival mode where it is almost indestructible. So some animals even live, here is an example of a fish that lives 8,145 meters under the surface of the ocean, which is quite extreme. And the life goes down to 10, 11 kilometers. So no ocean is, or no part of any ocean is without life, which is kind of extreme when you think that we can dive maybe 40 meters and then we're dead without a capsule. And here just I have to shortly mention the moon Io, which is not considered as life, potentially life-bearing, but extremophile maybe could survive there. There is sulfur, there is heat, maybe not much water, but I don't know. But it still should be looked at. Then there is something like ultraviolet habitable zone. I already briefly mentioned that ultraviolet can be good for life and it can be bad for life. So there is an optimal level of ultraviolet, and here it is differentiated with the atmospheres, how much is going through the atmosphere. So also that depends a lot on the planet itself and not only on its distance from the mother star. So as an outlook, habitable zones are a very coarse approximation of where you may find liquid water on a surface. It is about the surface, that's one thing. And it greatly depends on the planet itself, on its atmosphere, on its size, whether you look on the surface or the inside. So it's always good to look more closely. But of course, if you have a million stars and you have to choose one planet that could be habitable to look at it more closely, you certainly will will go into a habitable zone to search further before you invest tons of money. You may find life outside the habitable zone, or most likely no life inside the habitable zone. And again, simple life has a much wider habitable zone than complex life. That's something, these three things should be kept in mind. Something I didn't talk about in my channel yet was the planet Mars. And I like this Hubble Space Telescope picture of Mars, especially because you can see the water on Mars. And here is Valles Marineris, and here are some of the large volcanoes, and here is Olympus Mons, the largest volcano. So maybe in a later video we will also talk about Mars and its activity, its water, and if it could still have life, or how long it could have had life in the past. People also say we have a lift going from Mars to the Earth and from Earth to Mars, which is meteorites. But of course, it is not clear if life can survive a long time in the solar system between Mars and Earth before they come to the Earth and heat up in the atmosphere and still survive. We don't know that. But this lift actually exists because every century a couple of meteorites that are coming are actually from Mars. And these are some of the sources I used. Thanks a lot for the attention.